In this final video about determining wind load, we'll discuss the SANS 10160, which is the South African code for determining, or the portion of the South African code for determining wind load. And a link to this in the regional map as well are provided in the textbooks for the course. So before we dive into this code specifically, we need to find our basic regional wind speed from the map in section 5.5.2.2. And we'll note that this is going to replace our 100 mile per hour regional basic wind speed we've been using for the AASHTO and the ASCE guidelines that we've been getting from maps of the US, because we have a map of South Africa that includes Eswatini. We can use that map to get our regional basic wind speed, which we'll read off the map. You can look at that in the textbooks, but we'll read 40 meters per second, or about 90 miles per hour off that map. So not too different. In the map, it labels Swaziland because it's an older map, but this is the same value for Eswatini. And now this needs to get adjusted to a nominal wind speed, VZ, which is based on these 5 characteristics: the mean return period, the terrain category, the local effects, height above the ground, and the class of the structure. So we'll start with 5.5.2.3, which is the mean return period, and we just take this as 50 years based on the use and occupancy of the structure. In 5.5.2.4, we can determine the terrain category as category 2 for mostly open plains with some wide obstructions. This is a pretty conservative estimate and often an accurate estimate for some of our sites in Eswatini. 5.5.2.5, we can assume we have a fully developed wind profile and that local effects are not considered, and this is ultimately a conservative assumption to make. And then 5.5.2.6, we will find that the structure, or we'll determine the class of the structure as C, which is for main structural elements that are greater than 50 meters in either width, height, or depth. And we'll use this to determine the wind speed multiplier KZ to be 0.99 for 15 meter heights. And we'll use that in conjunction with the structure class, the terrain category, the mean return period, to read that off a table 5. So this gives us our nominal wind speed VZ, which is going to be 39.6 meters per second. And then moving on, you might recognize this variable from the other codes. We will transform this into a wind pressure on our structure. So our free stream velocity pressure, QZ, is calculated with Kp, which is taken as 0.6 for sea level from section 5.5.3.1. This is conservative because Kp is based on air density, which decreases with altitude. So we have a heavier wind blowing on our structure at sea level. So it's going to create more force, or more pressure. And then our surface pressure for the building, PZ, is just going to be our QZ modified by CP, which is taken as 1.0 in this case for cylindrical surfaces, and this comes from table 14. So both of these pressures come out to around 941 newtons per meter squared at this point. And then finally, the force on our structure is our effective area, AE, multiplied by our velocity pressure and our force coefficient. Using table 15 for a long, short rectangle, we get a force coefficient of 1.9. And I've drawn a little diagram here. Here's our D and our B, and our B over D is greater than 20, so we read 1.9 from table 15. And with our effective area epsilon, which we determined in the previous lectures for the W1 walkway detail, this equates to approximately 0.76 kilonewtons per meter. And now if you play around with the elevation modifiers and the site class, we can get anything from 0.5 to 0.9 kilonewtons per meter for wind loading on our structure, and we know that we're in the ballpark with that 0.5. It might not be the most conservative value to use, but we're still within that ballpark of the right number, so we know that our head's in the right place when we're calculating this value, and we use our engineering judgment, and it's really the designer's choice with some of these unknowns moving forward if we do need to calculate the wind load on the structure.